Okay. Lecture 25, only 3 more classes after today, and they're really just 2 subjects I wanted to cover. Conservative vector fields today, and on Monday, Green's theorem in the plane. So let's talk about a vector field. So we have a vector field F, which is a function of 2 or 3 variables. And unlike a scalar field, for every vector, let's say in the plane, x, y, we get another vector in the plane, say given by functions f and g. Or if we had a function of 3 variables, f of x, y, z, the vector field gives us a vector in R3, a 3-dimensional vector field. So that's what a vector field is. And we know one way to get a vector field. So suppose that phi, let's say we're working in 2 dimensions, phi of x, y is some scalar function. So from the scalar function phi, we can create a vector function, which is the gradient of phi. So this function is called the gradient of phi, and it's a vector field. So the vector field has first coordinate, which is the partial of phi with respect to x, and the second coordinate is the partial derivative of phi with respect to y. And if we were in 3 dimensions, so where we had phi is a function of x, y, and z, then the gradient of phi would be a 3-dimensional vector field, partial phi with respect to x, partial phi with respect to y, and partial phi with respect to z. So for example, if phi of x, y, z are equal to x squared y plus x e to the z, for example, then the gradient of f phi, you differentiate this with respect to x, you get 2xy plus e to the z. You differentiate this with respect to y, you get x squared, and you differentiate this with respect to z, and you get x e to the z. So from a scalar field, the gradient of your scalar field is a vector field. And if you had the vector field, say it was equal to this, 2xy plus e to the z, x squared, x e to the z, this vector field is the gradient of the function phi, where phi was defined like this. So some vector fields are gradients of scalar fields. And there's a condition that will always be satisfied if a vector field is the gradient of a scalar field. So suppose you have a vector field F, which is the gradient of a scalar field phi, where phi has at least 2 continuous partial derivatives, or we're the second partial derivatives, where the second partial derivatives exist and are continuous. So in the example we just looked at, here was the function phi. Here were the first derivatives. The second derivatives are also continuous. The second derivative with respect to x, y, or z of any of these functions is still continuous. And we know that if we have the partial of phi with respect to x and y, and the partial of phi with respect to y and x, that is, if we take the partial derivatives of phi with respect to x and y in the 2 possible orders, if these are continuous, then they're equal. Or another way of saying that is the second partial of phi with respect to x with respect to y is the same as the special second partial of phi with respect to y and with respect to x. So suppose f is the gradient of a scalar function. So let's look at the two cases separately of 2 dimensions and 3 dimensions. Suppose that f has is f of xy, g of xy. And suppose this is the gradient of some function phi. That means the partial of phi with respect to x is f of xy. The partial of phi with respect to y is g of xy. But then if we differentiate the partial of phi with respect to x and then differentiate it with respect to y, that's like the partial derivative of f with respect to x. And if we take the partial of phi with respect to y and then differentiate with respect to x, that's the partial of g. Sorry, we take this and we differentiate it first with respect to x. The partial of phi with respect to x is f. If we differentiate this with respect to y, that's the partial of f with respect to y. If we take g of xy and we differentiate it with respect to x, we get the partial of g with respect to x. But if the second partial derivatives are continuous, then they're equal. So then partial of y, partial of f with respect to y equals the partial of g with respect to x. So let me just summarize that. So if we have a vector field f, which has coordinates f and g, then the partial of f with respect to y equals the partial of g with respect to x. So for example, if f of xy were the vector field x squared y and xy cubed, so this is f and this is g, the partial of f with respect to y is x squared. The partial of g with respect to x is y cubed. These aren't equal. So this field is not the gradient of a scalar field because it doesn't satisfy this necessary condition. And in fact, this necessary condition is sufficient. If the partial of f with respect to y equals the partial of g with respect to x, then f is the gradient of a vector field. And let's see how we can find that. So let's take an example. Suppose I have a vector field f, and at xy, it's equal to, let's say, 2xy cubed and 3x squared y squared. So this is a vector field. For every pair of numbers, or for every vector xy, we have a vector given by this. So this is my function f, this is my function g. That is, f of xy is 2xy cubed, and g of xy is 3x squared y squared. If we take the partial of f with respect to y, we get 6xy squared. If we take the partial derivative of g with respect to x, we get 6xy squared. These are equal. So for this vector field, f partial of f with respect to y equals the partial of g with respect to x. And I claim that this condition is sufficient to prove that f is the gradient of some vector, some scalar field phi. So this is going to be the partial derivative of phi with respect to x, comma, partial derivative of phi with respect to y. And we want to compute phi. So what this says is that, so f, of course, f is 2xy cubed, 3x squared y squared. So this says that the partial derivative of phi with respect to x is 2xy cubed. And we want to find phi. Well, let's take the antiderivative. So phi is the integral of 2xy cubed with respect to x. What is that equal to? So phi is equal to, so y is a constant, y is fixed. The integral of 2x, we get x squared y cubed plus some constant. But the constant means constant with respect to x, so it could be a function of y. So phi is x squared y cubed plus a constant, any function of y. That is, if you take phi to be this for any function of y, if you differentiate with respect to x, you get 2xy cubed plus 0. But then if this is phi, then the partial of phi with respect to y, which we know is 3x squared y squared, if you differentiate this with respect to y, you get 3x squared y squared plus c prime of y, which means the derivative of c with respect to y is 0, which means c of y is some constant c. So phi is any function is x squared plus y cubed plus any constant. And if we just want to find one phi that works, we can just take the constant to be 0 and say that this function, this vector field, is the gradient of this function phi. I should say, just so we're learning the right words, you say a vector field F in 2 or 3 dimensions is conservative, or is a vector field F is a conservative vector field if F is the gradient of some scalar function phi, or some phi. And in this case, the scalar function phi is called a potential function or F. And if you've taken first year physics class, for example, where you learn about electric fields and magnetic fields, or let's just say electric fields, there's something called electrical potential, and this phi is exactly the potential function when F is the electric field. In any case, these are the important words. If you have a vector field, it's called conservative, that is the gradient of some scalar field. And that scalar field is called a potential function. So this is the situation for a vector field in 2 variables. It's slightly more complicated for a vector field in 3 variables. So suppose we have a vector field in 3 variables. F is x, y, z. So this is going to be a 3-dimensional vector. The first coordinate will be F, second G, third coordinate H, where these are functions of x, y, and z. And this is conservative if this is the gradient of some scalar function phi of x, y, and z. So let's look at an example. No, okay, sorry. So which means that if this is conservative, the gradient of phi is partial phi with respect to x, partial phi with respect to y, and the partial derivative of phi with respect to z. which means if the vector field is conservative, F is the partial of phi with respect to X, G is the partial of phi with respect to Y, H is the partial of phi with respect to Z. Now, if this is satisfied, if I take the partial of F with respect to Y, that's the partial of phi first with respect to X and then with respect to Y. If I take the partial of G with respect to X, that's the partial of phi with respect to Y and then differentiate it with respect to X. And if these second derivatives are continuous, the partial of phi if you differentiate first with respect to X and then with respect to Y, you get the same function as if you differentiated, or when you differentiate first with respect to Y and then with respect to X. So these are going to be equal. So the partial of F with respect to Y equals the partial of G with respect to X. Similarly, if I take F and I differentiate with respect to Z, that's the partial of, that's phi differentiated first with respect to X and then with respect to Z. And if this is continuous, and if the partial, and if you take phi and differentiate with respect to Z and then with respect to X, these are going to be equal. But H is equal to the partial of phi with respect to Z. So if I differentiate H then with respect to X, I'm taking phi, differentiating it first with respect to Z and then with respect to X, which means that the partial of F with respect to Z equals the partial of F with respect to X. That's the second condition that has to be satisfied. And the third condition that has to be satisfied is if I take G and differentiate with respect to X, differentiate with respect to Z, that's the partial of phi with respect to Y and then differentiate it with respect to Z, which again, if the second derivative are continuous, is the partial is phi differentiated with respect to Z and then with respect to Y, which is H differentiated with respect to Y. So we get the partial of G with respect to Z equals the partial of H with respect to Y. So if your vector field is conservative, these three conditions have to be satisfied. And the converse is also true. If these conditions are satisfied, then we have a conservative vector field, right? Let's look at an example. Suppose I take the vector field F in three variables, which is equal to, I'll make it more interesting, 2xz plus 3x squared y. And the second component will be just z. Z plus x cubed. Differentiate with respect to x, differentiate with respect to y. And the third component will be x squared plus y. So I claim this vector field satisfies satisfies these three conditions. So this is my function f, this is my function g, this is my function h. So if I differentiate f with respect to y, I get 3x squared. And if I differentiate f with respect to z, I get 2x. If I differentiate g with respect to x, I get 3x squared. If I differentiate h with respect to x, I get 2x. So the partial of f with respect to y equals the partial of g with respect to x. So this first condition is satisfied. The partial of f with respect to z equals the partial of h with respect to x. So this condition is satisfied. Suppose I take the partial of g with respect to z, that's 1. Suppose I take the partial of h with respect to y, that's also 1. So the partial of g with respect to h, z equals the partial of h with respect to y. So this third condition is satisfied. So this is a conservative vector field. And once we know it's conservative, we have the following computational problem. Find the potential function phi, that is the scalar function phi, such that the gradient of phi is equal to this f. So if that is going to be satisfied, then so here we have f, which is 2xz plus 3x squared y, comma, z plus x cubed, comma, x squared plus y. And I want to find a scalar function phi such that this is partial of phi with respect to x, partial of phi with respect to y, partial of phi with respect to z. And we can try to find phi by integration. This says, if you look at the first coordinates, the partial of phi with respect to x is going to be 2xz plus 3x squared y. So that means phi is going to be an antiderivative of 2xz plus 3x squared y dx. It's going to be some function which, when you differentiate with respect to x, gives you this. And one such function is the integral of 2x is x squared, so you get x squared z. The integral of 3x squared is x cubed y. And then what kind of function gives you 0 when you differentiate with respect to x? Any function, let me give it a name, I don't know, r, which only depends on y and z. Because if you now differentiate this with respect to x, function that only depends on y and z is 0. So phi is x squared z plus x cubed y plus some function of y and z. Now, again, if we look at this, the partial of phi with respect to y is going to be z plus x cubed. But if I differentiate phi with respect to y, this phi with respect to y, I get x cubed plus the partial derivative of r of y and z with respect to y. So that says that the partial derivative of r of y and z with respect to y is equal to z. So r of yz is going to be the integral of z dy, which is z times the integral of 1 is going to be yz plus a function which doesn't depend on y, so call some function s of z. So what I have is that phi is x squared z plus x cubed y plus r plus yz plus some function that only depends on z. If I take the partial derivative of phi with respect to z, that's x squared plus y plus the partial of f with respect to z. And that's going to be equal to the third component of the vector field f. That's x squared plus y, which means the partial of f with respect to z is 0, which means s is a constant. So I can take the constant to be 0, and I found my potential function, x squared z plus x cubed y plus yz. Right? So this is kind of unpeeling the onion, going backwards. So we have vector fields, and now we have the notion of a conservative vector field. Now, one of the fundamental properties of a conservative vector field has to do with a line integral. So let's recall, suppose you have a curve C given by some function r of t, where t goes from a to b. So you have your function r of t. It starts at t equal to a. It ends up at t equal to b. So here we have this curve C. And we have a vector field. F. And we've defined the line integral of the curve F. So this is one way to write it. This is the line integral of the vector field. It really maybe should be called a curve integral, but this is along of the vector field F along the curve C. And how is this defined? So at any point on the curve, so here's r of t, and there's a tangent vector there, which is r prime of t. And if that's not 0, it has a length. If you divide by its length, a non-zero vector divided by its length is a unit vector. It's a vector of length 1. We call that capital T at t. So this is the unit tangent vector to the curve at this point. And at this point also, we have the vector field F. And what we want to do is we take the component of F in the direction of the unit tangent vector. So this vector in red, the component in that direction is, well, it's the inner product of F dot product with the unit tangent vector, which is the length of F times the length of t times the cosine of this angle. But this is a unit vector, so it has length 1. So this is also just F cosine theta. Or it's F dot product with r prime of t over the length r prime of t. So this is all just review. The line integral of F dr, this is the integral of F dot the tangent vector. So this is F dot r prime of t over the length of r prime of t dr, and this is really then the integral of F of x of t, y of t, z of t. These are the points on the curve. Dot product with r prime of t, x prime of t, y prime of t, z prime of t, dt from a to b. That is the formal way we calculate a line integral. And the important theorem about conservative vector fields and line integrals is the following. Suppose F is a conservative vector field. And we have 2 points in the plane, say P and Q. So here's some region in the plane or in three-dimensional space, and F is a conservative vector field defined all over this region. Suppose we have two different curves, C1 going from P to Q. So C1 is given by some function R1 of T. And we have another curve that goes from P to Q, C2. So you could take your vector field and integrate it along the curve C1. So that's an integral along a curve that goes from P to Q. And we also could take the vector field F and integrate it along the second curve C2 from P to Q. And the important theorem, in fact, it's a complete description of conservative vector fields. If you have a conservative vector field, then these two integrals are always equal. So if you have a conservative vector field along any path from a point P to a point Q, the value of the line integral doesn't change. It's always the same. Let's see if there's a way to sketch a proof of this fact. So let's see what happens. So suppose here we have this curve C from P to Q. So C is given by some function R of T, where T is between A and B. So this is R of A, and this is R of B. And we have our conservative vector field F, which is the gradient of phi. Right? That's conservative means your vector field is the gradient of a potential function or of a scalar function. So the integral along this curve, F dr, what is this? This is the integral from A to B of F. So let's say F is, F at the point x of t, y of t, z of t, dot product with r prime of t dt. So that's equal to the integral from A to B of f of x of t, y of t, z of t. And this is dot product with x prime of t, y prime of t, z prime of t. This is the vector r prime of t dt. And what is this vector? So F is the gradient of phi. So this is the partial phi with respect to x, partial phi with respect to y, partial phi with respect to z, evaluated at r of t, dot product with this vector. So the dot product, this is the integral from A to B of phi x times x prime of t dt, plus the integral from A to B, phi y, y prime of t dt, plus the integral from A to B, phi z, z prime of t dt. And I want to say that this is the integral of the partial of phi with respect to x dx. And this is the integral of the partial of phi with respect to y dy. And this is the integral of the partial of phi with respect to z dz. So this would be phi of q minus phi of p. This is basically reducing everything using the fundamental theorem of calculus from first semester calculus. What we're going to get is phi at q minus phi at p. So just take this as a summary or as a theorem that we're giving without proof. But the proof is in the text, but I don't have the text to show you. So here is the following theorem. If f is the gradient of phi, then the integral from p to q of along any curve f dot dr is phi evaluated at q minus phi evaluated at p. So maybe in order to try and make this a little bit more coherent, let's take an example. See what happens. Suppose I take phi to be the function x squared y. So the partial of phi with respect to x is 2xy. The partial of phi with respect to y is x squared. So if I take f to be the vector field, which is the gradient of phi, which is 2xy comma x squared, that's my vector field, and it's conservative. So let's go into the plane, and let's say for fun, we take our curve to just be the straight line from 0, 0 to 2, 1. So what's a way to parametrize this? Just so to make the number, just so to avoid fractions, let me do it slightly differently. Suppose I take the straight line from, actually, let me just do it like this. My curve is the straight line from 0, 0 to 1, 1. So, and one way to parameterize that line is that r of t is equal to t comma t. T goes from 0 to 1. So when t is 0, we're at the origin. Along this straight line, y equals x, you're going along the line y equals x, and when t equals 1, you're at 1, 1. So let's try to calculate the integral along this curve of f dr. So this should be the integral from 0 to 1 of two xy comma x squared dot product with r prime of t dt. Well, r prime of t is 1, 1. So this is the integral from 0 to 1 of 2xy plus x squared dt. Along this curve, x of t equals t, y of t equals t. So this should be the integral from 0 to 1 of 2t squared plus t squared dt, or the integral of 3t squared dt from 0 to 1, which is t cubed from 0 to 1, which is 1. And this is also equal to, if phi is x squared y, phi of xy is x squared y, phi of 1, 1 is 1, and phi of 0, 0 is 0. So this is phi of 1, 1 minus phi of 0, 0. It's when you integrate along this curve, this is the value of phi here minus the value of phi there. So that's the calculation of one line integral. Let's take another curve that goes from 0, 0 to 1, 1. Suppose we take the curve y equals x squared. Right? Perfectly nice curve as you're going along a parabola. So let's take a look at that. So let me draw my picture again. 0, 0, 1, 1. And this is the curve where r of t is given by t squared. That is, y, which is t squared, is x squared. 0 less than or equal to t less than or equal to 1. So now my curve is from 0, 0 to 1, 1, is this curve going along the parabola. And again, my vector field F is what? Let me write it down again. F was 2xy x squared. Was the gradient of phi, where phi was equal to x squared y. And now along this curve C, I want to calculate the line integral f dot dr. So along this curve C, so along C, r of t is t squared. So x of t is t, and y of t is t squared. So I'm taking, this is the integral from 0 to 1, f of x of t, y of t, dot product, what is r? So r of t is t squared. R prime of t is 1 comma 2t. I'm taking the dot product with r prime of t dt. So this is the integral from 0 to 1. What is f of x? It's 2xy comma x squared dot product with x prime of t, y prime of t dt. This is the integral from 0 to 1, 2xy x prime of t plus x squared y prime of t dt. X is t and y is t squared. So this is the integral from 0 to 1, 2 times t squared, and x prime is 1, plus x squared, which is t squared, times y prime of t, which is 1, dt. So this looks like the integral from 0 to 1 of 2t cubed plus t squared dt. The integral of 2t cubed is 2t to the 4th over 4, plus the integral of t squared is t cubed over 3, evaluated from 0 to 1, which doesn't look good. This is a half plus a third, which is 5/6, and I wanted it to be 1. So let me just go back and double check what I did here. So I have x squared y, 2xy, and x squared. So this is the gradient of the function phi. I have the curve from 0 to 1 parameterized by t comma t squared as t goes from 0 to 1. So this is r of, all right, here's a mistake. R of t is t comma t squared. R prime of t is 1 comma 2t. So x prime of t is 1, y prime of t is 2t. So this is 2xy x prime plus x squared y prime of t, that's 2t squared plus t squared times 2t. So I have 2t cubed plus 2t cubed. This is 4t cubed dt. If I integrate 4t cubed, I get 2 to the 4th from 0 to 1, and that's equal to 1, just what it's supposed to be. So, except for the fact that my writing is illegible and so on. This is a nice example of the theorem that a line integral of a conservative vector field only depends on the initial and the endpoints of the curve. So the general fact is that if we have f, a conservative vector field, so it's the gradient of phi, and you have r of t, t goes from a to b, where r of a, the starting point, is some point p, and r of b is the ending point q. This is p, this is q, and here's my curve. The integral of f dr from p to q, along the curve, only depends on the initial point p and the start and the ending point q. This is going to be phi of q minus phi of p. So it doesn't matter what curve you take or how you get there, no matter what curve you integrate along, if your vector field is conservative, the result just depends on the potential function evaluated at the endpoints. Now, there's a very pretty corollary of that. First, there's the following fact. Suppose we have r of t, where t going from a to b. So you have some curve, c, which goes from r of a to r of b. Now, you could reverse that. You could take the curve going in the opposite direction. Let me just call that curve minus c. And for the integral, the line integral of a vector field, the integral along a curve c, f dr, is always the negative of what you would get if you go in the opposite direction. So minus f dot dr, called the c prime, where c prime is c going backwards. So I can start at a p and go to q like this, or I can start at q and go backwards along this curve to p. So those two different line integrals are the same in absolute value, but they differ in sign. And what that says is the following. Suppose we have a closed curve, C. In a closed curve, the starting point equals the endpoint. So if you have a curve that looks like this, you go along the curve, but you end up where you started. This is R of A, the starting point is equal to R of B, the ending point. This is what we mean by a closed curve. And suppose I take, and when you have a closed curve, sometimes to indicate the curve is closed, when you write the line integral, you put a little 0 on the integral sign. That's just to remind you that you're really going like around a circle. In any case, you start and you stop at the same place. Now, if I call this point P, and I take some other point Q, I could write this as the integral from P to Q plus along this curve. I'll just write it like that. Plus the integral from Q back to P. which is the same as the integral along, let's call this part of the curve C1 and this part of the curve C2. So this is the integral along C1 and the integral along C2. So this is the integral along C1 of the vector field. And this is minus the integral along C2 going backwards. F dot dr. That is, I can go from P to Q along C1. I can go from Q back to P along C2. But if I reverse C2, I'm going from P to Q in the opposite direction. So I'll call that C2 prime. And the integral along C2 prime, well, is plus the integral along C2 prime. No. The integral along C2 is minus the integral along C2 prime. But C2 prime is an integral from P to Q. If F is a conservative vector field, if F has a potential function, this first integral is phi of Q minus phi of P. But the second integral is the same. It's also phi of Q minus phi of P. And when you subtract, you get 0. So we've now proved the second fundamental fact about a conservative vector fields. If F is conservative in any number of dimensions, 2 or 3, is conservative vector field, and C is any closed curve, then the integral of this vector field along this closed curve is always 0, right? Because you're starting and ending at the same place. So we have two very important facts about conservative vector fields. One is that the value of a line integral from a point P to a point Q is independent of the path. It has exactly the same value no matter what path you take. And the second fundamental fact is that if you integrate a conservative vector field around a closed curve, you get 0. Okay, so those are the basic facts I wanted to describe today. Let me just repeat one other factor, the thing that we started off by saying. The definition of a conservative vector field is that it is the gradient of a scalar function. And such a scalar function is called a potential function for the vector field. And if you have a conservative vector field, then you have some conditions on the partial derivatives of the coordinates. If those conditions are satisfied, the vector field is conservative. And then, by successively using integration from the vector field that you know is conservative, you can calculate a potential function for it. And any two potential functions differ just by a constant. So all of this is very reminiscent of the fundamental theorem of calculus, and this is in many ways an extension of the fundamental theorem of calculus from 1 dimension to 2 or 3 dimensions. Okay. Now, normally I would do some examples from the book. I just made up a couple, but since I can't get the book today, that is all, I believe, that we're going to do.
Excuse me,
The very
Professor?
last topic that we cover, which I'll cover on Monday, will be Green's theorem. Is there a question?
Professor, I have a question. Will it be this weekend or until next week that we'll be able to get the final study guide
So I'll have the study guide together over the weekend.
over the weekend?
So
Okay.
you'll have it for a couple of weeks, for 2 weeks.
Okay. Thank you, Professor.
When is the final exam?
The final is, let's see, I know I posted it on Blackboard, and it's the final which we get, which was determined by the Lehman College final exam schedule. So ours is actually early, I believe. When is it? Let me see if I can find the final exam schedule, which I had posted somewhere.
I think I found it. I think it's December 19th at 11:30.
Yeah, I think you're right. It certainly is 11:30 to 1:30.
Yeah, I think I found it. Okay. Thank you. It's gonna be in the same classroom.
Yes, yes.
Okay, great. Thank you.
Professor, will we have like a formula sheet like last time, or like are we allowed to bring the one that you gave us last time for the exam or no?
I will prepare a comprehensive formula sheet.
Okay,
All right, but it'll be more than what was given last time.
thank you, Professor.
Yeah.
Professor, I have a question, but I'm gonna need to talk to you, I guess, privately.
Okay, so we'll wait till everyone logs off and then we can talk. If you have a few minutes, so that'd be fine. Okay, well, have a good weekend. See you on Monday.